Hello, ladies and gentlemen, and welcome to whatever on earth this is supposed to be, a physics presentation, because we do physics. Okay, first things first, amplitude modulation. In every...
Just for the record, the topic is broadband and mobiles.
What he said, meet my glorious assistant. Amplitude modulation. We have something called a carrier wave. This is basically whatever it is that we have that is going to be carrying our information. And in order to do this, you need to vary the radio frequency signal, or the carrier wave, again, depending on what you're actually doing. Variation, modulation, and action, ladies and gentlemen. And there are two ways you got to do this. The first is your amplitude modulation, where the amplitude of the carrier wave is varies towards the sound signal. The alternate method for this is frequency modulation, where the frequency of the carrier wave is varied according to the sound signal. There we go. So, amplitude wave versus sound signal. The other one is varying the frequency according to the sound signal. Sounds simple, right? Amplitude versus sound. Broadband. Way back when, you had dial-up internet. It was terrible. You had to pretty much use your phone to try and download everything. The thing is, with the information you're trying to download, is a lot of ones and zeros. Well, zeros and ones. Yes, zeros and ones. Damn it, binary. If there's a lot of them, then they can't all be that close together unless you've got a high frequency. And that's where broadband comes in. It squishes everything together, makes it fantastic. You get more downloads, everyone's happy. Cell phone. It's a phone that makes and receives calls over a radio link while you move around. Where we get the cell from, whereas we in England call them mobile phones, thank you Yanks, is because there's a cellular network. Which, funnily enough, I'm going to scroll all the way down here and show off what something else looks like. That's your base station, essentially. And what happens is that you get a load of those arranged hexagonally, and each one produces 3 different signals in this hexagonal shape. And then what happens is they put these base stations, basically, get the pun, in this honeycomb shape, where they're linking up with 3 other signals so that you always have the best frequency. And that's that.
Right.
Hang on. Wait, not done yet. Uplink and downlink. You get satellites and stuff in space. Uplink, you send information to them. That's the communication going up. The communication going down is downlink. Easy peasy. Or so you think. Half and full duplex. A duplex is a communication system that works 2 ways. In both directions. Not just 2 going one way, both directions. One going forward, one going backwards. Full duplex, that is exactly the case. You can communicate simultaneously. It's a telephone. Both can speak and hear completely whilst it's happening. In a half duplex, you get your 2 clearly defined paths and channels, and you communicate to each other, but you can't do it simultaneously, like those walkie-talkies you had when you were a little kid. And we then, I'm going to finish off my little pieces here and there, I guess. Mobile phones, different generations, 1 generation, 2 generation, 3 generation. Difference between 1 and 2 is pretty much that you were analog back in 1G, 2G digital, 3G, higher rate of transfer. On to my learned friend over here.
Right, to continue then, with regards to cell phones, there are different things that can affect the signal strength for it. Numerous different ones. Physical obstructions, things like walls, even people in some cases. Network range. Thank you, dear. Network range, how far the actual network tower's signal can get to, and the distance between the devices. If I'm going to call someone over on the other side of the world, it ain't going to be very good quality. Wireless network interference, if everyone's sending different wireless signals, they're all at the same frequency, they're all going to hit each other, it's going to make it a bit more of a problem to actually communicate with them. Network usage, again, more people using the network, less likely to actually get anywhere with it. And then you've got poorly deployed antennas. If they're out the way, if no one's going to use them, and there's, again, a large distance, not any useful. And local environment, if you stick an aerial deep down in the bottom of a hill, not very good place to get any signal out of there. Less obvious ones includes backwards compatibility, and that phones aren't as efficient at sending signals and receiving back in the olden times. And so because those phones are still in use, you've still got to have them have your actual network still use those old capabilities instead of new and polarized signals, as all the signals are polarized that are used. And if your phone's not going to be aligned to actually in the same direction, you're going to lose the signal. You can also calculate this, or how much signal is being lost the further away you get, by using the inverse square rule, which states that intensity is inversely proportional to the square of a distance. So, if I double my distance from the base station, then the signal will be at quarter strength. Phones generally was also a thing here about analog to digital conversion. Analog, of course, analog is what we mostly used back in the olden days, but now we want digital because it's easier to use. And this is converted from analog to digital by using PCM, which is pulse code modulation. This works by taking the analog signal and sampling it at regular intervals and at regular time intervals. And this then is these are then look at words.
Oh, them wordings.
Oh yeah. Then the frequency is then quantized, as you can see from this lovely diagram here, which is where this line here would be our normal analog wave, and these are the intervals, and this is where they're then quantized into binary by the frequency, which is how it works out. So in this case, those intervals become 0, 1, 0, 1. So this wave would be 0, 1, 0, 0. Then, God, this is a terrible diagram I've drawn. And so on and so forth. Have you got anything else to add, Dave?
Nah, we're good. If at any point you got confused, there are notes there. Pause the video, have a look, read them. Done.
Peace.